So molecular orbital theory. This is the last bonding theory we're going to cover. This is often abbreviated MO. Where's the MO theory? Molecular orbital theory. In this theory, instead of looking at orbitals that are on individual atoms that are localized, we're looking at orbitals for the entire molecule that are delocalized. So the Schrödinger equation gives us the wave function for the orbitals. And even for a very simple molecule, we can't solve the Schrödinger equation. It's impossible. So we use trial functions. You use a trial function, you see how that works, and then you tweak the function. It's an iteration process. They use computers to figure out what is the best trial function for the Schrödinger equation. It's the one with the lowest energy. So you optimize for the lowest energy. This is our approximation of what nature does. We can never outdo nature. Nature minimizes the energy on those orbitals perfectly. We're just trying to describe what we observe. So all of that is, the calculation business is definitely beyond the scope of this class. So we're not going to think of it in terms of quantitative equations. We're going to look at more the conceptual, qualitative stuff. So one way that they do this with the computers is called a linear combination of atomic orbitals. That's a lot of syllables, so LCAO. This is a weighted linear sum of the valence atomic orbitals of the different atoms that are in the molecule. These give us the simplest trial functions that work reasonably well. So we're taking the valence atomic orbitals of all the atoms in the molecule and combining them together. So in valence bond theory, we had the hybrid orbitals on individual atoms. So we just looked at the central atom, and we took its atomic orbitals and we hybridized them. So this is kind of the same idea, but instead of hybridizing orbitals on a single atom, we're combining the valence orbitals for all the atoms in the molecule. Those combinations are delocalized over the entire molecule. In valence bond theory, the hybrid orbitals are still localized on a single atom. So that's a big difference between these two theories. Any questions yet? So let's look at hydrogen. Always good to start with the simple molecules. So H2. So we're going to look at molecular orbital by combining these two 1s orbitals from each atom. So when we combine these two, we can get this sort of a shape. This is lower in energy than the individual orbitals on the atoms. This is called a sigma orbital because it has a cylindrical, symmetrical shape. Just like we talked about the sigma bonds in valence bond theory, they were symmetrical. This is a sigma orbital. So it's called sigma 1s because it's a combination of 1s orbitals. This is a bonding orbital because it lowers the energy. If something's going to bond, it has to have lower energy. If you're bringing things together and it has higher energy, that does not promote bonding. So we take the two orbitals from each hydrogen atom, combine them together, and we get this bonding orbital. Any questions? The next molecular orbital is achieved by summing the 1s orbital on one atom with the opposite phase of the 1s orbital on the other atom. So here what we were doing is we're combining these two in phase. Remember, the orbitals really are like waves. They're wave functions. And so waves can constructively interfere or they can destructively interfere. So this is constructive interference of the two orbitals. This is like destructive interference of the two orbitals, where we're subtracting them or we're adding the opposite phases. And that gets us what's called an anti-bonding orbital. So this is called a sigma star 1s. The star tells us that this is an anti-bonding orbital. This causes the energy of the molecule to be higher, and so that's against bonding, so it's called anti-bonding. Any questions? If you're thinking that this is weird, yeah, this is weird. So we've got the two atomic orbitals adding together, making two molecular orbitals. Just like with valence bond theory, if you start with two orbitals, you're going to end up with two orbitals. You call that conservation of orbitals. Never heard anybody call it that, but I just made it up. So you can combine those two in a destructive way or a constructive way. Destructive way increases the energy, destructive increases the energy, constructive decreases the energy. Those are kind of backwards, aren't they? This reduces the energy of the molecule because it has a high electron density between the nuclei. That's going to bring those nuclei together. It's going to promote bonding. This anti-bonding orbital has a node between the two nuclei. There's a place between the two nuclei where the electrons are not present. That does not facilitate bonding. In fact, that is against bonding, so that's the anti-bonding. So we draw diagrams, molecular orbital diagrams. And this shows how two hydrogen atoms can lower their overall energy by becoming a hydrogen molecule, H2 molecule. So the way we draw these things is we put orbital diagrams for each of the atoms on the outside, and then in the middle we show how those combine to molecular orbitals. And as is our convention, energy is increasing as you go up. So here's the orbital diagram for one hydrogen atom. Here's the other hydrogen atom. We've drawn this electron with a negative spin or a downward spin because we're going to combine these two together. They are going to spin pair when they get into the molecular orbitals. So for 1s orbitals, when we combine them, we get a sigma 1s orbital that's bonding, so lower in energy, and we get a sigma star 1s orbital that's higher in energy. We take those two electrons and we fill in the molecular orbitals just like we filled in orbitals when we were learning about quantum mechanics. They're going to take their own orbital with a positive spin, and then they're going to pair up before they go into higher energy orbitals. So those two electrons are going to go in here. Questions? I know, this is weird. It's weird stuff. We have something we call bond order. The bond order helps us to know if this molecule is actually going to exist, if this bond is going to form or not. So the bond order for a diatomic molecule, the good news is we are only going to look at diatomic molecules. We're not going anywhere past that. So for a diatomic molecule, we're looking at the number of electrons in the bonding molecular orbitals. We're subtracting the number of electrons in anti-bonding orbitals and dividing by 2. So for H2, we just looked at its molecular orbital diagram. We have 2 minus 0 divided by 2, so that equals 1. So go back here. What we're doing is we're counting how many electrons are in bonding orbitals. Well, there's the one bonding orbital, it's got 2 electrons. So that's 2. We're going to subtract the number of electrons in anti-bonding orbitals. There aren't any. So 2 minus 0, and then divide by 2. So the bond order for H2 is +1. If the bond order is positive, a chemical bond will form, because that indicates that the electrons are going to have a lower energy when the bond is formed than they would as individual atoms, so a bond will form. The higher the bond order, the stronger the bond. So if your bond order is 2, that bond is going to be stronger than something with a bond order of 1. The bond order can be 0 or negative. In those cases, the bond will not form. And the bond order can also be a fraction. It could be like 1/2 or 1.5. Those are possible as well. Any questions?
Would it ever not be 0?
The number in the antibonding?
Yeah.
Yeah, definitely. There's many situations where it's not 0. Just not hydrogen. We'll get there. So let's look at He2. So before we even look at that, does helium form diatomic molecules? No. I've told you before, helium doesn't form any compounds. So why would we get He2? Well, we're just going to see what happens, okay? We can draw a molecular orbital diagram for anything, and we look at the bond order, and that's going to tell us whether it actually exists or not. So we've got a helium atom over here. It has 2 electrons in the 1s orbital, and a helium atom over here. And when we combine these 2 1s orbitals, we get a bonding orbital. Come on, pointer. Bonding orbital and an anti-bonding orbital, just like we did for hydrogen. But now we have 4 electrons to put in there. So the first 2 electrons go into the lowest one, and the next 2 electrons go into the higher one. So then when we calculate the bond order, we're looking at number of electrons in bonding orbitals. That's 2. We're going to subtract the number of electrons in non-bonding, anti-bonding orbitals. That's 2. So 2 minus 2 is 0, divided by 2 is 0. So for He2, the bond order is 0. That tells us this bond is not going to form. And it doesn't. Because 2 helium atoms bonding together will not lower their energy, so there is no reason for them to form a molecule. Any questions?
Will it increase their energy?
I don't believe that this will increase their energy at all. It just won't decrease it. So they just won't. Some of them would actually be increased in energy by bonding, and so those are like really, really not going to happen. We can also look at diatomic ions. So an He2+ ion, we haven't seen anything like that before, but we can recognize what it is. 2 helium atoms, the positive charge means they're missing 1 electron. So we've got this same overall diagram, but here now we have a helium atom here and a helium+ ion there, meaning it only has 1 electron. So the overall diagram is the same, but now we have 3 electrons to put in. So 2 go into the bonding orbital, 1 goes into the anti-bonding orbital. So when we calculate the bond order for this, we end up with 1/2. So we have, what is that? We have 2 electrons in the bonding, right? And minus 1 electron in the anti-bonding orbitals, divided by 2, that gives us a bond order of 1/2. That is a positive number. That tells us that He2+ should exist, and it does. Is it common? No, but it does exist. When you make it in a lab. The question is, where does it exist? Yeah, I don't think we find that in nature, but you can make it, and it will hang together. So, summary. We approximate molecular orbitals as linear combinations of atomic orbitals. It's an approximation. The number of molecular orbitals that form is equal to the number of atomic orbitals. So if you start with 5 orbitals, you need to end up with 5 orbitals. When you take 2 atomic orbitals and combine them, You get two molecular orbitals. One will be lower in energy, called a bonding orbital. One will be higher, called an antibonding orbital. Because we're taking those two wave functions and adding them together in phase and out of phase. So we're doing constructive interference and destructive interference. When we put the electrons in the molecular orbitals, we're going to do the same thing we did with the atomic orbitals. You put the electrons in the lowest energy molecular orbitals first, with up to 2 spin-paired electrons. We're going to follow Hund's rule. If you have several that are the same energy, you put them in with positive spins first, and then when they have to pair up, you put them in as negative spins. And in order for this to have for you to be describing a stable bond, we need to have a positive bond order. In other words, there need to be more electrons in the bonding orbitals than in the antibonding orbitals. More contributing to bonding than fighting against it.
What determines how many bonds you can make?
What determines how many bonds you can make? Well, we're not actually going to be looking at forming multiple bonds between two atoms here. We're keeping it simple. So let's use molecular orbital theory to predict the bond order in H2+. And then ask, is that going to be stronger or weaker than an H2 bond? So we need to draw the molecular orbital diagram. So let's start with each of the individual atoms. So here's a hydrogen atom here, a hydrogen atom here. But this is H2+. So that means it's missing an electron, right? So one of these has to be H+. Doesn't matter which side you put it on. I'm going to put it over here. So how many electrons does a hydrogen atom have? 1. So we put this electron spin up in the one orbital. How many electrons does a hydrogen ion have? None. 0. So this is just empty. When we combine these orbitals, we get one orbital that's lower in energy and one that's higher. So here's one that's lower. Here's one that's higher. So this is called a sigma 1s, and this is called a sigma star 1s. And a lot of times we'll do dashed lines here to show which atomic orbitals those came from. Energy is always increasing as we go up. So these are the molecular orbitals in the middle. We're going to take the electrons that were in the atomic orbitals and we're going to put them in the molecular orbitals. Here we only have one electron. And they're going to go in the lowest energy ones first, so we're going to stick it right there. And so this is H2+. Okay, so there's our diagram. We're supposed to use this to predict the bond order. So bond order is the number of electrons in bonding orbitals. How many electrons are in the bonding orbital? 1. And we're going to subtract the number of electrons in antibonding orbitals, which would be 0. And we're going to divide by 2. And so this has a bond order of 1/2. Is this predicted to exist? Yes.
Yeah.
Positive bond order above 0 should exist. Is that bond going to be stronger or weaker than the bond in H2? Do you remember what the bond in H2 was? The bond order for it? It was 1. So the bond order for H2 is 1. The bond order for H2+ is 1/2. Which one is stronger? H2. The larger the bond order, the stronger the bond. So the bond order's 1/2, and this should be weaker than H2. Any questions? So we just looked at period 1, hydrogen and helium. Now we're going to look at period 2. So diatomic molecules have 2 atoms. Homonuclear diatomic molecules. Homo means the same. Nuclear refers to the nucleus. So these are the same atoms, the same elements in the diatomic molecule. So it's, Li2 or N2 or O2. We're not looking at 2 different elements here. We're looking at 2 atoms of the same element. So the next one up is number 3, which is lithium. So lithium has, again, we're looking only at valence electrons. We're not looking at core electrons. So lithium has 1 valence electron. It's in the 2s orbital. So here we have a 2s orbital with 1 electron. Over here we have a 2s orbital with 1 electron. Those s orbitals are going to combine into a sigma and a sigma star 2s. One's bonding, one's anti-bonding. So we get the molecular orbitals in the middle. Then we take these electrons and we put them into the orbitals. They're going to go first into the bonding one, the lower energy. They're going to spin pair, so 1 up and 1 down arrow. And that's all of our electrons. So we can calculate the bond order for this guy. So 2 electrons in bonding orbitals, 0 electrons in anti-bonding orbitals, divided by 2. So the bond order for this is 1. This is predicted to exist, and it does. Only in the gas phase, but it does exist. Questions? Yeah.
I'm confused with how you would figure out the bonding and anti-bonding.
How many electrons in there? Okay, so how do you figure out where the electrons go, how many are in anti-bonding and how many are bonding? Well, we're always going to get a bonding orbital that's lower in energy and an anti-bonding orbital that's higher in energy. And just like when we filled in doing orbital diagrams for an individual atom using its regular, 2s, 2p, etc., we're going to put them in the lowest energy first. So this is just like a modification of the quantum hotel, where this room's cheaper, so the electrons are going to go in there first. And then they're going to go in there only if they have to. Does that help?
So if there was 3, then maybe one anti-bonding?
Yeah, if we had 3 electrons here, the third one would have to go into the anti-bonding. Exactly.
And we're only going to see up to 4.
Well, for 2s orbitals, we can only have up to 4 electrons, yeah.
Are we going to go to p orbitals?
Yes, we are going to go to p orbitals. Woohoo.
Oh, so it follows like the same thing.
Yes,
P6.
this is very much related to quantum mechanics. It comes from quantum mechanics.
Okay.
It's just looking at it in terms of what happens with a molecule.
Okay.
So let's look at Be2. So beryllium has 2 valence electrons in the 2s orbital. Here again, we have 2s orbitals combining. We get a sigma 2s and a sigma star 2s. One's lower in energy, one's higher in energy. Now we have 4 electrons, and so we put the first 2 in here, and the next 2 have to go up there. The bond order here is going to be 0. Oops, did not mean to do that. So the bond order is there's 2 electrons in bonding orbitals and 2 electrons in anti-bonding orbitals. And we're going to divide by 2, and so that equals 0. A bond order of 0 says that this is not going to be a stable molecule. This bond is not going to exist. And that is consistent with experimental findings. So if we get to boron, now we have to look at the p orbitals. So let's look at 2 p orbitals the px in both of these atoms. So p orbitals have two lobes, one with a positive phase, one with a negative phase. So we can put these two together just like we did the s, where we're adding, getting constructive interference, or subtracting, getting destructive interference. When we put these two together so that these lobes have the same phase, then these constructively interfere, and so we get this big bulgy lobe here between the nuclei, and that's going to promote bonding. If we put them together out of phase, we get a node in the middle, and the parts between the nuclei shrink really small, and we've got big lobes on the outsides pulling them away, basically. So this is a bonding orbital, that's an antibonding orbital. Every time you combine two atomic orbitals, you're going to have one that's lower in energy and one that's higher in energy. This is also a sigma orbital because it's symmetrical. So just like valence bond theory, when we had the overlap end to end, if you look down the axis from the one nucleus to the other nucleus, what are you going to see? You're going to see it's round. You're going to see the big bulgy blue part here, and then if you're at that end, you'd be able to see the little red part. But it's going to be symmetrical, right? It's cylindrical, sigma. It's a sigma bond, sigma orbital. So this is sigma 2p and sigma star 2p, because this came from a 2p. This came from combining 2p orbitals. And we got the other two p orbitals, and those are oriented differently. So py, here the orbitals are parallel to each other. They're perpendicular to this bond axis. So how can these interact? Well, they can interact positively or negatively. The bonding orbital, you're going to get this big red lobe here and a big blue lobe over there. But the density is between the nuclei, and so this promotes bonding. When you add them together out of phase, or you could think of that as subtracting them, you end up with a big old node in the middle and lobes on the other sides of the nuclei. This is an antibonding orbital. These are not cylindrical. So if you look from this end down to that end, you're not going to see one big circle. You're going to see that one on the one side and another one on the other side.
Is that how the like dinosaur egg like magnet things work?
The dinosaur magnet things. I don't know what you're talking about.
You would like flap them together and make a weird noise. And they're like,
Well, those are magnets, and so.
do these have charges? Are these talking about charges at all, or?
Well, there's charges involved,
Like what
but these are waves, right? Do you remember that video I showed you with the box, the guy that took the box out on the beach? Were you here for that? You need to watch that video. It's good. Waves can interfere constructively or destructively, and so here they're adding together. They're making things bigger, and here they're making things smaller.
Waves?
The waves, yes. Yeah. It's a bit much to absorb, I'll give you that. But when we look down the axis here, one nucleus and then the other nucleus exactly beyond it, what we're going to see is these two orbitals like this. This is not a sphere, it's not cylindrical overall, right? So this isn't a sigma orbital, this is called a pi orbital. Just like in valence bond theory, when we had the side-to-side overlap of p orbitals, we call that a pi bond, right? So these are pi orbitals. There's pi 2p, that's a bonding, it's lowering the energy. Pi star is increasing the energy, it's an antibonding orbital. And then there's another pair of p orbitals, and those are also going to do this side-to-side thing. And so you can get bonding and antibonding. And again, these are pi orbitals. So there's some similarities here between valence bond theory and molecular orbital theory. There are similarities because we're describing the same things. We're just interpreting and explaining why they happen a little bit differently. Okay, so I'm sorry about this, but it's how it is. The relative energy ordering for the molecular orbitals that we get from the 2p atomic orbital combinations is not the same for all molecules. They determine this computationally. What we're going to try to remember is that B2, C2, and N2 are going to have one order, and O2, F2, and Ne2 have a different order. So boron, carbon, and nitrogen are the first three in that P block. Oxygen, fluorine, and neon are the last three. So what we think of as the typical energy ordering is the sigma orbitals are both the lowest. The bonding is the lowest in energy. The antibonding is the highest in energy. And those pi molecular orbitals are in the middle, with the bonding being lower in energy than the antibonding. So this is what these would look like. So we've already looked at what happens when we overlap s orbitals. This is what we think of as normal expected order. We've got 3 p orbitals here and 3 p orbitals there from the 2 atoms. When we combine these, one of each of these overlaps end to end, forming a sigma bonding orbital and a sigma antibonding orbital. And then the other two are going to add together or subtract side by side, and so we're going to get 2 pi 2p bonding orbitals and 2 pi star 2p antibonding orbitals. These are antibonding because you put electrons in there, that increases the energy, which fights against bonding. So that's the expected order. It's nice and symmetrical, isn't it? The sigma's on the outside and the pi's in the middle. Yeah.
There wasn't pi's in the s orbital, were there?
No.
Okay.
No. Pi only happens with the p orbitals.
And what do pi's represent then? 'Cause
Well,
like there's sigmas.
So we get the pi molecular orbitals from the side to side. And we get the sigma molecular orbitals from an end-to-end overlap, or adding.
Okay.
And this is sigma because it's symmetrical around that bond axis. These guys are not symmetrical, they're not cylindrical around this axis. There's a piece over there and there's a piece over here. So those are the pi. So, one way you could think of it is, here's like, it's got, turn it on its side, that's pi. It's got those 2 pieces, right? Whereas this one, you look at the end of it, and it looks round like sigma. So looking at the end, this is kind of like a sigma. It's a circle, right? And these guys, there's these 2 pieces like the legs on the letter pi. It's not exactly why they called them that, but if it helps you remember, that's awesome. So this is the expected order. This is what boron, carbon, and nitrogen do. And how do you remember that those are the ones that do it? We think, be careful now. B for boron, careful for carbon, now for nitrogen. Be careful now. These have a different order. So the S is the same. What's different here is the ordering of the orbitals from the 2p. So now we have the pi being lowest, pi bonding, and then sigma bonding, then pi antibonding, and sigma antibonding. So the antibonding orbitals are the same, but the pi bonding the bonding orbitals have switched. So that's the difference between these two, is these are different. That's the only difference here. This one has sigma on the outside, pi's on the inside. Here, the lower two, the bonding orbitals are switched. And so what happens here is it has to do with s orbitals and p orbitals mixing together. So for these, the boron, the carbon, and the nitrogen, we've got increasing mixing of the s and the p orbitals, and that's why we get a switch in the order. Because here the sigma orbitals from the s are down here, and when we have the p orbitals interacting with each other, they're going to mix more. That doesn't even make a whole lot of sense to me. Why do we even talk about it? That's embarrassing. Okay, so there's more interaction between the 2s and the 2px orbitals for boron, carbon, and nitrogen. There's less interaction here. This is more typical, this is kind of unusual, and so we think of this as the exception. So we're going to look at all 6 of these homonuclear diatomic molecules. So the first 3, be careful now, those have one ordering, where the pi bonding orbitals are lower in energy than the sigma bonding orbitals. And then we have pi star and sigma star. Over here, less overlap, less interaction between S and P, and we've got the sigma 2p being lowest in energy, and then the pi 2p. These are the same order. So here, for boron, we've got 2 boron atoms. They each have 3 electrons, right? So we put 6 electrons in here. 1, 2, 3, 4, 5, 6. We're just filling from the bottom up, and these are going to take their own orbitals because they can. And then we can calculate bond order. So the bond order for this one is the number of electrons in bonding orbitals. So this is a bonding orbital, and these are bonding orbitals. So that's 4 electrons in bonding orbitals, and there are 2 electrons in antibonding orbitals. So 4 minus 2 is 2, and then we divide by 2, so this has a bond order of 1. C2 has a bond order of 2, because we've increased the number of electrons in bonding orbitals relative to the antibonding. N2 has a bond order of 3. The extra 2 electrons also go into a bonding orbital. We can see here as the bond order increases, the energy of the bond increases, and the bond length decreases, because a stronger bond is shorter, and a longer bond is weaker. A weak bond is longer. Then when we get to these guys, this order reverses. Now oxygen, you're going to have a total of 12 valence electrons in the molecule. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Compared to nitrogen, this has 2 more electrons in antibonding orbitals, and so its bond order is less than that for nitrogen. And we see a corresponding decrease in bond energy and an increase in bond length compared to nitrogen. For fluorine, adding 1 more electron from each atom, those are going into antibonding orbitals, and now the bond order has dropped to 1. Bond energy decreases, bond length increases. When we get to neon, Ne2, now we've got all of these orbitals filled. We have an equal number of bonding and antibonding orbitals with electrons, and so the bond order is 0. We can't calculate a bond energy or a bond length because this bond doesn't exist. Any questions? You guys don't like this, do you? I don't blame you.
Sigma star 2s would be non-bonding.
Sigma star 2s is non-bonding or anti-bonding because it's higher in energy than the atomic orbitals. And it has a star. The star is what tells us, really. So this came from, on each side, I'll stick it in here. So the 2s in the middle, and when we combine two of those atomic orbitals, one's going to be higher in energy, one's going to be lower. This group up here came from 2p orbitals. And they would be, in energy, they would be right in here. And so we get a total of 3 that are lower in energy and a total of 3 that are higher in energy. So the higher energy are the anti-bonding, the lower energy is bonding. It's a good question. Period 2, homonuclear diatomic molecules. Well, this is exciting. I don't remember what these videos are, so this will be an adventure. Oh, that's what it is.
When liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid. When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic.
See how it's sticking in there?
Paramagnetic substances have unpaired electrons.
Oxygen?
Liquid oxygen. Mm-hmm.
How's that made?
You get it really cold.
Oxygen? Just the air?
Yeah. Liquid nitrogen is they get it from condensed air. Just make the
Drink it, you'll be fine.
no. No. You guys didn't go to the chemistry show on Friday, did you? There was a chemistry show on Friday.
Nobody knew that there was a chemistry show on.
Right, because the club did not make the flyers and put them up. No, she knew about it, she didn't go. So they did some demos with liquid nitrogen. So liquid nitrogen is really, really cold. That's what they use to freeze warts off of your skin, but they've got it in a little can and they just apply a little bit. And it freezes things, and when things get super cold like that, their properties change. So what Mr. Balo does is he'll take a flower, like a rose, and you stick it in the liquid nitrogen, and you pull it out, and it looks okay, and then you tap it on the counter, and it shatters into little pieces. And you can do that with hot dogs, with balloons, with all kinds of things. So if you were to stick your finger in there, your finger would freeze solid, and it would freeze so solid that if you tapped it on the counter, it would shatter into pieces. So drinking liquid nitrogen would be really, really not good. I mean, you talk about brain freeze, that would be the ultimate brain freeze. It would kill you. It really would. So yeah, you definitely don't want to use it. But did you see what was going on in that video? So it looks like they're pouring water, right? And the liquid nitrogen just pours right through the magnet like you would expect a liquid, right? The liquid oxygen, though, sticks between the magnet. It hangs out there. Did you see that? So what's up with that? Well, so we know from experiments like that oxygen is paramagnetic. It is attracted to magnetic fields. We talked about paramagnetic and diamagnetic before. Paramagnetism is a result of unpaired electrons. Well, Lewis model gives us this illustration for oxygen. Do you see any unpaired electrons? No, there's no unpaired. There's non-bonding, but they're all paired up. Right. Now, don't you like Lewis theory now that we've seen all these other complicated things? Doesn't that look so nice and simple and kind of friendly? It's just letters and lines and dots. And then we have valence bond theory, which is those crazy balloon construction things, right? Valence bond theory, we've got overlap between p orbitals on the oxygen, this sigma bond here, and then we've got side-to-side pi bond overlap here. There aren't any unpaired electrons there either. So both of these models predict that oxygen will be diamagnetic, like nitrogen, and should just pour straight through that magnet. But that's not what happens. So obviously something is lacking in both of these models. Molecular orbital theory. So let's go back and look at the molecular orbital diagram for O2. There they are, the unpaired electrons. Molecular orbital theory predicts that oxygen is paramagnetic. It also predicts that B2 is paramagnetic. The rest of these, here's liquid nitrogen, you make it liquid, it's diamagnetic, it should not be attracted to a magnetic field. That makes sense? So molecular orbital theory is fixing something that's lacking in those others.
So why are they lacking?
She raised her hand.
So what if you had one of those electrons paired up? Would it still be paramagnetic?
So what if you had one of these paired up and only one unpaired? It would still be paramagnetic because all it takes is one unpaired electron for it to be paramagnetic. Now you ask your question. You forgot.
Well,
Why are they lacking?
yeah,
I think was your
yeah.
question. Well, they're lacking.
In the Lewis.
Yeah, so why doesn't that show it? Well, the Lewis model is an oversimplification of what's actually going on. And valence bond theory is also an oversimplification. But they're great because they are more simple than this, and yet they still explain an awful lot of stuff. We are just doing diatomic molecules. You can do molecular orbital theory for big, complicated molecules, but then it gets to be a big, complicated, hairy mess, right? So what we want you to understand is that this theory exists to have an idea of what the theory is about. And at the very end, I'm going to show you how molecular orbital theory also explains something else that's really important for OChem, organic chemistry. So let's do another example here. We're supposed to draw a molecular orbital energy diagram for the N2 plus ion and determine its bond order. Then we'll look at the rest of those questions. So the way you approach this, so N2 plus, so we've got nitrogen and nitrogen, but since there's a positive charge here, that means we're missing an electron, so one of these has to be an N plus ion, right? And then we're going to draw the orbitals for each of these atoms. So for nitrogen, the valence electrons, we have 2p and we have 2s, right? How many valence electrons does a nitrogen atom have? 5. So we'll put those in there. 1, 2, 3, 4, 5. And the orbitals over here for the N plus are the same orbitals, but N plus only has 4 electrons. 1, 2, 3, 4. Okay? We have to combine these into their molecular orbitals. And this never works out spatially for me. It's frustrating. So I'm going to put these two pretty close together because I need a lot of space that I don't have for the p orbitals. So when those s orbitals overlap, we get a sigma 2s and a sigma star 2s. This one's lower in energy, it's a bonding orbital. This one's a little higher in energy than the atomic orbitals, so it's an antibonding orbital. I took 2 atomic orbitals, combined them, I get 2 molecular orbitals. Then I'm going to take these guys and combine them. And let's see here. You like that? I like that. Move them around. Oh, you can't see that. Okay, there. I just moved them. I didn't have no space. Sorry, I was in. Never mind. When the p orbitals overlap, one pair overlaps end to end, making a sigma bond or a sigma orbital, and the other two overlap side by side, making pi orbitals. This is nitrogen. So nitrogen is one of those three that does it weird. Be careful now. And so we don't have the regular order, which would be the sigmas on the outside and the pi's in the middle. So this one has the pi 2p orbitals down there, and then the sigma 2p, and then the sigma, no, sorry, not the sigma, then the pi star, oh gosh, and then the sigma star, and that's 2p. That make any sense? And so we've got 3 orbitals that are lower in energy and 3 that are higher in energy. The good news is I'm not going to make you draw these diagrams on an exam. Yeah, you're welcome. You need to be able to identify the correct one. So you'll see in the practice exam questions what it might possibly look like. Basically, I'll give you diagrams, and you'd have to choose the correct one. So you do have to understand it, but you don't have to draw it for me, because I don't want to look at your drawings. I don't like looking at my own. Okay, so we drew these. They're messy and ugly, but we got it done. There's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. So once we have our molecular orbitals, we're going to put them in using the same rules that we did for atomic orbitals. Going lowest first, so 1, 2, 3, 4, 5. This next one is going to take his own orbital. 6. Then they have to pair up. 7, 8, 9. Any questions about that? Fill them from the bottom up, just like we did with the quantum hotel. They go right side up first, and then if they have to pair up, they flip and face down. So now the questions about this. Determine the bond order. So bond order is number of electrons in bonding orbitals. So this is a bonding orbital, and these are bonding orbitals, and that one's a bonding orbital. The ones without the stars. So we've got 2, 4, 6, 7 in bonding orbitals. How many in anti-bonding orbitals? 2. And that's divided by 2. So 7 minus 2, this is going to be 5 halves, or 2.5, right? So do we expect this to be stronger or weaker than N2? Question.
Where did you get the 7 from?
I got the 7 here. By looking at the bonding orbitals. So that one, and these, and this one. Those are bonding. There are 7 electrons in those orbitals. The ones without the stars. Yeah.
Are you divided by 2 because of the anti, or just always divided by 2?
You always divide by 2. We're really dividing by 2 because we've got two atoms here, so we're dividing by 2. Any other questions? So what's the bond order for N2, not N2 plus? Well, we could go back and look. Here's N2. It has a bond order of 3. So if this one has a bond order of 2.5, is it stronger or weaker than N2? It's weaker because its bond order is smaller. So this is weaker than N2. Is this diamagnetic or paramagnetic? It's paramagnetic. It has 1 unpaired electron. Nitrogen doesn't. But this one has 1 unpaired electron, so it's paramagnetic. It will be attracted to a magnetic field. Questions? What about heteronuclear diatomic molecules in the second period? So hetero means different. So here you have 2 different elements bonding. So here's one of my favorite molecules again. No. We've got oxygen and nitrogen. Oxygen's more electronegative. So that means that its atomic orbitals are going to be a little bit lower in energy than the nitrogen. And so this one's going to be a little cockeyed here. The lower energy atomic orbital contributes more to the bonding orbitals and less to the anti-bonding orbitals. The higher energy atomic orbitals contribute more to anti-bonding than to bonding. So we put the electrons in here. Nitrogen has 5 valence electrons. Oxygen has 6. That's a total of what, 11? So we've got 2, 4, 6, 8, 10, 11. So we can look at that, we can calculate its bond order, we can predict whether it's paramagnetic or diamagnetic. It's paramagnetic. Looking at hydrogen fluoride. So fluorine is so electronegative compared to hydrogen that all of its atomic orbitals are lower in energy than hydrogen's 1s orbital. So then that gives us some weird things happening where we've got the 2p orbitals for fluorine overlapping with the 1s orbital or combining with the 1s orbital. And so we're going to get an end-to-end overlap from one of these p orbitals. So we get a sigma bond or a sigma orbital here and a sigma star here because you always have to have one bonding and one anti-bonding. And then these two are not going to do anything because hydrogen doesn't have any p orbitals to overlap with these p orbitals. Its 2s and 2p orbitals are so much higher in energy that they are not going to interact with fluorine's atomic orbitals. So then we end up with something like this. Okay, use molecular orbital theory to determine the bond order of the FO- ion. Is the ion paramagnetic or diamagnetic? So let's see if I can do this better this time. So we've got 2s and 2p. So be careful now is boron, carbon, and nitrogen, fluorine and oxygen are not in that category. So they're going to have what we think of as the regular order. So here we've got our sigma and sigma star from the 2s. And then now for these p orbitals, we're going to have the sigma 2p is the lowest, and the sigma star 2p is the highest. And then in the middle, we've got the pi 2p and the pi star 2p. So these are coming from those guys. And these are from the S. So let's put fluorine over here and oxygen over here. We've got a negative charge, so one of these has to have an extra electron. In terms of writing the molecular orbital and finding the bond orders and everything, it doesn't matter which one you give the negative charge to. I'm just going to give it to fluorine because fluorine's more electronegative. So F minus would have how many valence electrons? 8. So 1, 2, 3, 4, 5, 6, 7, 8. And oxygen has 6, right? 1, 2, 3, 4, 5, 6. So we have 8 plus 6, we've got 14. So we're going to put 14 electrons in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What's the bond order? Well, we have to look at the bonding orbitals. So that's bonding, that's bonding, that's bonding. How many electrons in the bonding orbitals? 8. How many in the anti-bonding orbitals? 6. Divide by 2. So that's a bond order of 1. Is it paramagnetic or diamagnetic? It's diamagnetic. All of its electrons are paired up. It will not interact with a magnetic field. Any questions? So we're not going to draw the orbital diagrams for polyatomic molecules, but we're just going to look at some things about them. So Lewis structure and Lewis theory and valence bond theory for ozone. So we talked about how we do resonance with Lewis structure and how experimentally we know that these bonds are actually equal in strength and length. You could call them a 1.5 bond. Lewis bond theory has no way to describe that other than just doing the two extremes and putting a double-headed arrow. Valence bond theory also does not take care of resonance. So when we draw the bonding scheme for ozone, this predicts a single bond over here and a double bond over there. It doesn't describe what we actually observe. But molecular orbital theory does. In a molecular orbital diagram for this, we've got orbitals combining the p orbitals from all 3 of those atoms, and so we get this molecular orbital that's delocalized over the entire molecule. And that's how we can get the 1.5 bond. We have this bond that's spread out over 2 bonding areas. So it's 1 bond divided by 2, it's like a half bond. But it's delocalized. So molecular orbital theory describes what we observe, that ozone has equivalent bonds. Any questions? Benzene is a molecule you'll run into in organic chemistry. So in benzene, Lewis theory, the best we can do is just describe this as alternating single and double bonds around this 6-membered carbon ring. And you can put the double bonds there, or you can put them in the other positions, and you say it's resonance, it's between these two. Molecular orbital theory describes this as we've got these delocalized molecular orbitals that are over the entire molecule. And this better represents what we observe, that benzene is highly symmetrical and all of the carbon-carbon bonds are identical to each other. So that's right there. That's really why we had to talk about molecular orbital theory at all. Questions? Yeah.